We now begin our journey into a study of probability. And it's interesting, probability got its genesis with gamblers. That's the the wives' tale that's told when students first take a course in probability, in that it was gamblers. They tried to figure out what is the most likely outcome as far as their games of chance are concerned, right? But that then it has evolved into a very rich area of math, lots of important theoretical results that then lend themselves to so many different applications. And right, so we're gonna get some exposure to some of those ideas and applications. Um, and we begin now. So this video kind of sets the stage for what probability theory is, and for that we need to define quite a few things, but within the definitions I will give you certain examples to give you a better understanding of what each definition is saying. So where do we start? Well, we need to define the concept of an experiment. And so an experiment is it's a process that results in an outcome that cannot be predicted, so that cannot be predicted with any certainty. Right? So it's something that you do, it's a process that's done, and the outcome is not predetermined. You don't know for sure how this process is going to end, right? So, what are some examples? So, let me give you like just a few different examples to illustrate, the idea of an experiment. The simple act of tossing a coin is considered an experiment, right? Because you hold it, you flip it, and then it's flipping in the air, and you don't know how it's going to land. Is it going to land on heads? Is it going to land on tails? There is the uncertainty in terms of the outcome, right? Another simple one. You can see these are the ones that are associated with games of chance. So rolling a die, right? That is an example of an experiment. So, there are 6 possible faces on a die, usually numbered 1 through 6. You roll that die, you have no idea which face is going to land showing up, right? So there's that uncertainty. But then there are other things too, like measuring the diameter of a bolt, right? Again, with the example of a bolt, there might be some set specification that this diameter should be within, right? But how do we know if this particular bolt meets specification? Even so, there's usually a tolerance, so we don't know that precise diameter until we actually measure it, right? So here are just, these are just a few examples of an experiment. And the one thing they have in common is this random nature of their outcomes. All right? Now, speaking of those outcomes, something else we have to define, and this is called the sample space. And the sample space is the set of all possible outcomes, right? So notice we're using that word set. And now we have a very precise definition of what a set is. And so let's write that down. So the sample space is a set of all possible outcomes of an experiment. So everything that could potentially happen, we call that our sample space. Now, the analogy is, and we've dealt with this concept before in our brief look at set theory when we talked about the universal set. That's exactly what the sample space represents. So, to kind of help you see the connection between our topics, think of the sample space as the universal set. So basically, the analogy is what the universal set is to set theory, the sample space is to probability theory, right? Now, those two theories are not mutually exclusive, right? But I just, in terms of the terminology that we use, I wanted you to get that analogy. All right, so that's the sample space. Well, now it turns out there are different types of sample spaces, right? So what I'm going to do is do some more examples, maybe use one or two of the examples above, but then come up with maybe one or two more of experiments, and then we'll try to describe the sample space and then identify how the sample spaces are different. All right, so I'm going to make a table, and we're going to have one column I will state the experiment, and then the other column we will try to list or describe its sample space. Okay, so let's take, for instance, we'll take one of the first two up here, because they both have the same type of sample space, so I don't want to list them both. But let's say rolling, well, actually, let's use the tossing a coin, because this will illustrate a couple subtle differences in the types of sample spaces. So let's start with tossing a coin. Right? Let's be precise and say once. Well, if you toss a coin once, you can end up with one of two outcomes, a head or a tail. So here is our set, and I'll just use H for head and T for tail, right? Very simple. The sample space is relatively small. It just consists of two elements, either a head or a tail. Now, I'm going to modify this experiment just a little bit and show you what a significant impact that has on the sample space. So here's the experiment. We're going to toss a coin until a head is observed. Right? So we're going to keep flipping the coin until we see a head. Once we see the head, we'll stop. Well, let's see if we can list it. Well, let's reason through all the possibilities. We could observe the head on the first toss. So it could be a head, and then the experiment would end, and this would be the outcome. Otherwise, we could toss it once and get a tail, toss it again, and then see that head, right? Or we might have to toss it once, twice, thrice before we see that first head. And then again, let me do one more possibility here. You could have a tail, a tail, a tail, and then a head. So I'm basically using the notation when I concatenate the letters. It's like, this is what I observe first. So since I haven't observed that head, I have to toss it again. and I still observe the tail, and then another tail, and then I observe a head, and then that's again another outcome, right? But in theoretically, we could continue tossing and getting a tail and never see a head. So I'm just going to do dot, dot, dot to indicate that this sample space is technically infinite, right? I can list the outcomes, I can definitely see the pattern, but there is no end to that pattern, right? Because technically, we can keep tossing and keep getting tails, 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 and never see a head, right? Now, how likely is that? Well, that's a big part of what probability is all about. We're now going to be, and we will get to that. We'll talk about what probability is. But here, if you notice, there's a slight change in how we define the experiment, makes a huge difference in the sample space, right? So a third one. Let's go back to that. Well, something that's similar to measuring, but instead of measuring the diameter, I'm going to say measuring contents, or actually, instead of using the word measuring, let's say weighing, right? So let's say we're gonna weigh. So weighing the contents of a box, right? Well, what could be that sample space? Well, it's a number, right? So since we're weighing something, so it's going to be a number. Well, what kind of number can it be? Well, it depends on our measuring device, right? And depending on the precision of this device, we could get a very precise weight. It could be to 1 decimal place or to 50 decimal places, right? And now the weight of an object, it can't be negative. I guess theoretically, you could say an object has 0 weight. That's one for the physicist. But yeah, so it seems like the sample space here would be the set of all numbers such that it's greater than or equal to 0. But then, I mean, we don't know how heavy it is. Is it 10 pounds? Is it 1,000,000 pounds? Is it, 1,000,000,000,000 pounds? We don't know. So technically, there is no upper bound on this sample space, right? And again, I can't list it. I can't list it like I did the H and the T here. I can't list it like I did this, right? And these 3 experiments and their corresponding sample spaces, it highlights the different types of sample spaces that we have to be aware of, right? So let me explain what those differences are. Both of these are, well, this one, let's start here. This one is a finite set. This sample space is finite. These two are infinite. They go on forever. However, this one is you could either say it's listable or it's countable, right? And this one is not, again, because it's like a continuum. It's that idea that there are no gaps between the different weights. They're all one part of essentially a number line. Now, it's not the entire real number line, because obviously weight can't be negative, but certainly positive and therefore infinite, but in a different way, right? So let me make a little, almost like a tree diagram. So sample spaces, what can we observe? Well, first, the sample space could be finite or infinite, right? If the sample space is finite, so then we can list the specific elements. If and then that list has to end. If the sample space is infinite, the ones that are listable, like the example of tossing the coin until we observe a head, where we can list them, but the list never ends, those are called countably infinite. So you could have countably infinite sample spaces, right? And the sample spaces that are associated with like weighing things and measuring things like a length or a volume, those tend to be uncountable. Right? Uncountable, right? And these are the ones that, again, essentially form a set of an interval, like a continuum. There are no breaks in it. But these, the finite ones, there you can list them separately, but the list ends. The countably infinite, you can list them, but the list never ends. And then the uncountable ones are not listable. You can't list them. If a sample space is finite or countably infinite, we say that that sample space is discrete. So these two are described as being discrete sample spaces because you can list them. You can say, okay, here are the two specific outcomes, or here are the infinitely many outcomes, but it's like head and then tail head and then tail head and so forth, right? If the sample space is uncountable, right, then we refer to it as a continuous sample space. So this one is said to be continuous, right? And the nice thing about this course is we are going to learn how to deal with all three of these types. And just kind of looking ahead, when dealing with sample spaces that are discrete, all you tend to need is basic algebra. When dealing with sample spaces that are continuous, what you typically need then is calculus, right? And so obviously what we're going to do, the idea is we're going to start with the discussion about discrete probability, talk about some of its properties and axioms and so forth. And then once we have that mastered, then we'll shift over. And not only are we talking about probability, but we get to use the beauty of calculus. All right? So this is an important sort of classification as far as the sample spaces, right? Now, a couple other definitions, again, to continue to set the stage. We need you'll hear this word a lot in probability, event. And the definition of an event it's very simple, and it utilizes, again, another concept from sets. An event is a subset of the sample space. Right? That's an event. So it's some subset. So it's one or more of the possible outcomes, right? And so to kind of put it in context, an outcome is basically it's sometimes referred to as a simple event where one thing happens, but in general, an event could be one or more, right? Because it could be any subset of your sample space, right? Now, so what is probability? So with all this said and done, what is probability, right? And what we're describing here is known as like a classical probability. But let me give you kind of an informal definition of a probability. It's basically it is a measure of the likelihood of some event occurring, right? Um, based on some experiment, right? So based on some experiment. Oh. So that's what probability is. We're measuring the likelihood of something. Right? So going back to like our a couple examples earlier with, for instance, the one where you toss a coin until you get your first head. What is the likelihood that you will need like 3 tries to observe that first head? Or what is the likelihood that it will occur on the 10th toss of the coin, right? Probability, we're going to learn how to associate a number with each of these events that will talk about their likelihood, right? And then we can say, well, something is more likely to happen than something else, but it's a quantitative thing, right? So classical probability. So classical probability is used when each outcome, so each specific outcome of the sample space is equally likely to occur. So outcome in a sample space, or let's just say each outcome is equally likely to occur, right? And that's kind of it's a theoretical thing, because what you're saying is you're basically asking yourself, if I were to perform this experiment, tell me how likely each of these events or outcomes are likely to occur, right? So here is the basic premise of the classical probability. So we use P of A to represent the probability that event A occurs, right? And the concept, the basic concept of classical probability is this: to find the likelihood that event A will occur, it's expressed like this, and then I'll tell you what these symbols mean. So I'm going to use a little n, A, n of A, and then divided by n of S. And the n here represents the number of elements in. So n of A represents the number of elements in that particular set. And then n of S, this would be the number of total possible outcomes, because it's referring to the number of elements in the sample space. Right? And by using this ratio, we're using this fraction to say, okay, if if outcome or event A has this many elements, what proportion of all elements do they represent? And that proportion affects the likelihood and hence the probability, right? So this is a simple, again, this is the classical way of doing probability. Later on we will talk about the statistical way of, now statistics is is basically you analyze the results of the experiment, whereas probability, you try to predict the outcome of the experiments. But we'll say a bit more of this when we go deeper into the particular course. All right. So let's do a couple examples illustrating this classical probability approach before we even put together any axioms. I think we will end with the axioms, but let's just do a few examples. And in each case, I will highlight the process of, again, figuring out this numerator, this number, and then also this denominator. But in general, the reason why those counting techniques are important, because in more complicated experiments, those counting techniques will give us a way of counting how many elements are in a certain set, or how many elements are in a certain sample space. So here is my first example. So toss two standard fair dice, right? So these are not dice that are loaded where, you know, it's more likely for one face to come up than the other. So these are all fair dice, and we're going to toss two of them. What is the probability? Right, so what is the probability that the faces shown, so that the faces shown sum to a prime number? Interesting. Right, seems like a nice problem. So again, here's the experiment. We're going to toss two standard fair dice, and we want to know what is the probability that the two faces that are showing, right, sum to a prime number. Okay, so the first thing I'm going to do here is let's see if we can figure out what the sample space is, right? So now, since these are two fair dice, it's almost like the sample space should be two-dimensional. So instead of just a list, I'm going to use like a table, almost like a matrix in a sense, and list them. So what I'm going to say is, let's do this. Right. So on the first die, so die 1, you can get a 1, 2, 3, 4, 5, 6. And similarly, on die 2, you can get a 1, 2, 3, 4, 5, or 6. So we roll them. We can get any of these on the first die, any of these on the second die, and then the rest of the experiment is then we're going to add up the faces that are shown. So what I'm going to do right up here, I'm just going to put that I'm going to do an addition, and what that means is whatever is in this row, again, I'm just going to add it to all of these. So for instance, if I observe a 1, if I roll a 1 and a 1, then the sum will be 2. If I roll a 1 and a 2, then the sum would be 3. And similarly, I can fill out the first row in here like this. Right? So here again, we're not done yet. We essentially have to fill out this entire grid, again, almost matrix-like structure with all these outcomes, and then that will be our sample space, because then we would have covered all the possibilities. So because it's addition, then it's pretty easy. It might be a little tedious, but here we go. So we're just going to fill it out all the possible sums of these two faces, right? 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, and 11, and then 7, 8, 9, 10, 11, 12. These are you can count them up, but it's easy. There are 36 different outcomes, or I should say, there are 36 different events, but some of the outcomes are the same. In other words, these are the two ways that you could end up with a 3. These are the 3 ways you could end up with a 4. These are the 4 ways you can end up with a 5, and so forth, right? So there are 36 here, right? So what we can say is, so this picture here represents the sample space. So our sample space has how many elements? Well, how many possibilities do we see here, right? There are a total of 36. 6 times 6, 36. Now, remember what A is. A is the event where we get or outcome where we get a prime number, right? So what I'm going to do is let's circle all the prime numbers in our table. So we know 2 is a prime, 3 is a prime, 4 isn't, 5 is a prime, 6 isn't, 7 is a prime, and you can see, lucky 7, you see how 7 occurs many times, and then the other prime number here is 11, right? So all the numbers circled in red, these are the ones that would represent set A, right? And there are all different ways we could get it. So of course, a prime number for us here is 2, 3, 5, 7, 11. And then let's count up how many of them. So the number, well, in fact, let me define A up here since I haven't defined it. So A is observing a prime. Right? Then this notation makes sense. So the number of ways I can observe a prime, let's count up all the red circles. So 3 and 4, that's 7, and 5, that's 12, and 2, that's 14. Right? So of all the possible outcomes, right, 14 of them will result in a sum that's a prime, right? So the probability, right? So the classical way of saying, even if you never picked up 2 dice, right? If you never tossed them, we could say with certainty that the likelihood of us observing a pair, if we were to perform the experiment, is the fraction 14 out of 36, which reduces to, what's that, 7 over 18, right? So it's less than 50%, right? And if you wanted to, you could write this as a percentage, and then that percentage again would represent the likelihood of us observing a sum that is prime, right? So I think that this is a nice example. This just gives you another illustration of how you can think about listing the sample space. We could have done it as ordered pairs and so forth, or we could have listed it as in our standard set notation. But having it in this 2-dimensional grid really, puts it at the forefront to say, okay, here's everything that can happen, and here is what we're trying to quantify in terms of getting this a sum that is a prime number. All right. So we're going to end by listing some important axioms of probability. Now, what is an axiom, you might ask? Well, an axiom is it's a self-evident truth, meaning it's something that we take for a fact, and we don't have to justify why it is true. Unlike a theorem that has to be justified, right? So let's end by talking about some axioms of probability. And again, an axiom is a self-evident truth. In a philosophical way, another example of an axiom for people of faith would be the existence of God, right? They don't need a formal proof. They just accept that God exists, right? So again, I don't want to get too philosophical or sound like a theologian or anything, but I just wanted you to get a sense of what an axiom is. All right. So there are three of them, and the first one is really simple. It says, so let S be some sample space, right? And once we say that, it means that S represents the set of all possible outcomes of some experiment, right? So we have our sample space. The first axiom is saying that is this: the probability of the sample space is 1, right? Because if you think about it, from our definition, remember we were saying when you're finding the probability of some event, you take the number of elements in that event and divide it by the number of elements in the sample space. Well, if you're taking the probability of the sample space, you'll have to have, I'll just kind of write it above, it would be this: it's the number of elements in the sample space divided by the number of elements in the sample space, and there's your 1. The other way of interpreting this, which is again more conceptual, it's basically saying if you perform the experiment, something has to happen. One of the possible outcomes must occur, and then we have this probability of 1 associated with it, right? So that's our first axiom. The other axiom is this: for any event, let's call it A, and that A is a subset of the sample space, then it turns out the probability of that event must be between 0 and 1, right? And it's because of this. Because events are subsets of the sample space, then these events can't have more elements than the sample space. So when you set up your fraction, when you set up your n of A over n of S, you're counting the number of elements. So you're never going to get something negative in your count, right? And the numerator can never exceed the denominator. So the largest this fraction can be is 1, right? So whatever method or techniques we come up with for probabilities, they have to satisfy this, right? So if I ask you for the probability of something occurring, you could never tell me 1.3, or you could never tell me negative 1/2. You can't have negative probabilities. You can't have probabilities that exceed 1, right? Your probability must be, so essentially the range, if you think of your probability as a function, the range of your probability function is the interval 0 to 1. You have to get one of those numbers whenever you assign a probability, right? Again, it kind of makes sense. The third one is this, and there are kind of two parts to it. So if A and B are mutually exclusive or disjoint, right? And we talked about those earlier. So if these are mutually exclusive events, so they have no elements in common, so mutually, mutually exclusive events, then if you want to find the probability of either A, excuse me, A occurring or B occurring or both, in other words, the probability of the union, since they have no elements in common, what you end up doing is taking all the, finding the probability of A, and then adding to that the probability of B, right? And that's if you know that they're mutually exclusive. If they're not mutually exclusive, we're going to have to figure out another way of assigning this probability. How do we compute it if they do have elements in common, right? Now, this axiom can be extended, so I'll just say more generally, right? If A1, A1, A2, A3, and so forth are all mutually exclusive events, right? So are mutually exclusive so that none of them have any elements in common, are mutually exclusive. Then if I have to compute the probability of A1 union A2 union A3 union dot dot dot, then it is the probability of A1 plus the probability of A2 plus the probability of A3 and so on, right? And again, really, so the number 3 seems a little bit more involved. It might seem a little less intuitive, but basically what it's saying is if the events have no elements in common and you want to find the probability of, of at least one of them happening, in other words, either A and or B, I'm sorry, A1 and or A2 and or A3 and so forth, simply add up their individual probabilities to get the total. In fact, this is sometimes referred to as the law of, I'm not going to say that law right now. We will talk about it in the future. But here are our axioms of probability, and they're simple, but they're profound in what they allow us to do. And going forward, we're going to derive some other properties of probability and then see how they are applied. So hopefully that kind of sets the stage for some really exciting work to come. So I'll see you in the future.